So you asked for data. I will provide some data. That's pretty good, but I will start with a short motivation. So the increasing demand for energy efficient solutions in all socially relevant areas is there. And also, of course, this trend is observed in the automotive sector. Strongly driven by e-vehicles as well, and the stronger energy efficiency requirements for all components means also the lighting systems. So alongside the functionality and the design, the sustainability of these systems will be an important aspect of system design. But we don't have to forget that the lighting systems are of great importance for safety and perception in nighttime road traffic. So the goal must be the efficiency enhancement of automotive lighting systems without compromising driving safety. And we see the operating time of the headlight as the most relevant phase for efficiency enhancement. And there were also some approaches for sustainability improvement during the operating time. So like Balleau already said, the replacement of halogen bulbs with LEDs in the light functions could reduce the energy demand, and also the low beam has a great efficiency enhancement potential. But the remaining question is, in which situations can the energy demand be reduced in a large manner? So the scope of this work is the analysis of traffic situations for the efficiency enhancement potential based on traffic situation, based on traffic statistics. And for that, we analyzed mainly the German traffic statistics and looked at different traffic situations, such as congestions, the rush hour traffic at dusk, the urban nighttime traffic, and also some traffic light situations. We started our considerations with the annual mileage for passenger cars in Germany, which is nearly 645 billion kilometers, and of that 645 billion kilometers, the nighttime mileage share is about 20%. So if you look at the congestion as the first traffic situation, we can say in 2019, so the year before the COVID pandemic, we had more than 700,000 congestions in Germany during the year. That means 1.4 million kilometers of congestions and 520,000 congestion hours. So we have around about 0.74 hours per congestion. To estimate the total duration of the congestions in a year, we estimated the passenger car length as 4.6 meters and a safety distance of about 2 meters. So we have 250.6 million vehicles that were in congestion situations during the year 2019. To have the total congestion duration for all included vehicles, we calculated 160 million hours, which are 127.6 million hours for the day, so 80% of that. And with the night time share, we have nearly 32 million hours that we drive or stand in congestions during the year. But which lighting functions could we adjust in that situations? What we could do during the day is to dim the daytime running lights, because in a congestion situations, no one needs the daytime running light for recognition of a car. And at night, we can turn off the low beam and dim the brake lights, because these light functions cannot fulfill their initial aim, their initial task anymore. So that would be the case for the congestions. And the second situation we looked at was the rush hour traffic at dusk. We have a share of commuters in the workforce. Of them, 68% commute by car. That means 31 million commuters per day, per working day in Germany commute by car to work and back home, of course. And the rush hour in Germany is between 6:30 and 8:30 a.m. and 3:30 and 5:30 p.m. So if you look at the sunrise and the sunset in Darmstadt, for example, we see that in the winter months, the rush hour and the dusk coincide. So we have 1/3 of the year that we commute in the dusk during the whole year, and then we had two assumptions which say that 2 hours commute time per day, 1 hour at the morning, 1 hour at the evening, and 250 working days per year. That means, and Elo, here's the data, 5.15 billion hours that we are traveling during the dusk in the rush hour. The adjustment for the light functions could be, like you said, the switching thresholds between the DRL and the low beam that are actually 1,000 and 7,000 lux due to the regulation. The third traffic situation we considered was the urban nighttime traffic. And the nighttime mileage in urban traffic, like I said, is 20%. And if we take the total mileage of nearly 645 billion kilometers and the urban share of 26%, we are nearly at 33.5 billion kilometers that we drive in urban areas during the night. So the total duration with average speed in urban traffic in Germany, about 27 kilometers per hour, is 1.2 billion hours that we travel in the night in the urban areas. Adjustments to the light functions could be to dim the low beam due to the stationary lighting, but to be able to do so, we need some insights. So we need to check the visibility conditions for safe detection of obstacles, and also we need to check the visibility conditions for the safe driving experience of the vehicle drivers. So there's some work to do still to see how we can dim the low beam and to which extent we can dim the low beam in the nighttime traffic in urban spaces. If you look, last but not least, at the traffic lights, we can assume a daily operation time of a passenger car of 0.75 hours per day and a time loss at intersections of approximately 10%. So if we then see what the total standstill time at red traffic lights per year is, with 48.5 million passenger cars in Germany, we can say it's 1.3 billion hours per year. In the daytime, 1.1 billion hours, which means 80%, and at the night, 265 million hours, which means 20% of the total mileage. So the adjustment for the light functions at the traffic lights for the day, there is no reasonable adjustment at all. But in the night, we can again dim the brake lights because we already have the signaling function by the traffic light itself. So we don't really need the full brake lights to signalize that we are stopping now. Now we have a look at 4 different traffic situations, but we need to compare them somehow. And for that, we took different parameters like the total duration per year that I showed already, and we also looked at the adaptable light functions that we could adapt, and we took the halogen power consumption to compare the traffic situations and not the lighting functions or the lighting systems or the technologies. And if you look at the effort for realization, you can say the sensors that we need are already present, all of them. And the activation could be on-off switching or a dimming electronic, so it's not a real effort to realize that. And as a comparison factor, we also calculated the energy saving potential for all of these lighting functions with the total duration per year and the power consumption of the standard halogen lamp for these light functions. And we can say it's pretty much. It's several gigawatt hours for each of these scenarios with small adjustments. There is no big effort that we need to put in there. But if we really want to have the winners, it's the rush hour traffic at dusk and the nighttime traffic in urban areas. Because here we have more than 100 gigawatt hours per year that we can save with small adjustments. And with that, I want to come to my conclusion. We considered different traffic situations from the traffic statistics in Germany for their efficiency enhancement potential. And my take-home messages: the rush hour traffic at dusk and urban nighttime traffic have the biggest potential, but all traffic situations we considered with simple adjustments have the chance to contribute to energy savings of several gigawatt hours. And that's it from my side. Thank you very much for your attention.